Hi, hello, and welcome to ECNG 3025 Discrete Signal Processing. The first few lectures that we're going to be going through today would be a review of general signals and systems. In particular, we would briefly touch on the continuous time system, and then we'll move on to the discretized or digital time system, which is going to be the main foundation for this course. So, as stated before, basically, continuous time systems are what you tend to deal with in real world scenarios, especially when dealing with like analog systems or whatnot. But because this course focuses more on the discrete and digital time systems in particular, this is what our main focus is going to be on. In particular, for discretized and digital signals, we're going to be observing this in this course, and for systems, we're going to be focusing more on discretized time systems. We also need to observe the periodicity and the unit step functionalities in order to understand how certain signal manipulations can work. So just as like a brief recap, as we can see here that we have an analog continuous time signal that is represented as a steel pen note. And we can see that there's some form of oscillation occurring that you can say it's characterized like a sinusoid signal. And if we decide to take the spectrum of this signal, we can see that in this case the frequency tends to be centralized around this general sinusoid frequency, indicating that most of the content of the signal is centralized around this frequency itself. One thing to note is that the steel pen note here is in the time domain when we're watching it on top, and the spectrum is represented in the frequency domain. Now, because we're focusing more on discretized time signals, we're going to be actually observing some signal manipulation in regards to this. So, the above here that we're watching, these signals are basically some examples of discrete time signals. The convention is to represent the signal as x of n, where n is in square brackets, and n represents the index at which the sample was taken for each one of these signals. Therefore, a delayed signal can be represented as x of n minus k, where k represents the delay. An inverted signal is noted as x of minus n, and a unit step would be u of n. So if we have a general signal here, for this first sequence, we can say that as x of n. For a delayed sequence, a delay means that the signal is shifted towards the right because it starts like k seconds later, or k indexes later in this case. So, in this particular case, what we can observe is that we no longer start at time equals 0 for x of n, but instead, for n equals 0 as the index for x of n. But now, because we're starting at the fourth index here, because this was at 0, 1, 2, 3, 4, this represents our k factor here because we're now starting at 4. And because that means we delay the signal accordingly, the shift represented is n minus 4 accordingly. If we decide to flip the signal around the x-axis, or i.e. if we decide to flip it vertically, that's represented by minus x of n. And the final signal that we're observing here is the unit step sequence, which is denoted as u of n. Please note that the unit step is defined that everything before n equals to 0, it's going to be 0. And everything at n equals 0, going forward, it's going to be 1. So just to recap a little bit, any discretized time signal is going to be represented as x of n, where n is in square brackets. A delayed signal is going to be x of n minus k, where k represents the delay. An advanced signal, where the signal is shifted towards the left instead, is going to be x of n plus k, where k represents the advance. A reverse signal means that the signal is flipped about the y-axis, or that it is flipped horizontally. It's going to be x of minus n. And an inverted signal, where the signal is flipped vertically, is going to be a minus x of n. And finally, the unit step sequence is that x of n is going to be 1 for any index of n of 0 and anything greater. And for n less than 0, the x of n values are just going to be 0. And this signal is denoted as u of n. So, the upper figure that we're observing here is a discrete time sinusoid, and basically you can see it's like a stem plot representing the samples that were taken from the real-world continuous time signal. The lower figure represents an exponential sequence, that is a discrete time exponential. This is an example of a real exponential, but there may be complex exponentials as well that may be represented a little bit differently, but for the purpose of this course we're dealing with only real components of any signal. We will not be dealing with imaginary components until like we hit like the fast Fourier transform in particular. The associated MATLAB code for each one of these signals can be seen here in the yellow block if you wish to generate it. So the upper figure here is what we refer to as an odd or anti-symmetric sequence. And mathematically, it needs to satisfy the relationship that x of n equals to minus x of minus n. What this means is if we start with the original signal here, x of n, and we flip it vertically and then horizontally, if we get back the same signal, this signal is an odd sequence signal. For our lower figure here, this is what we refer to as an even or symmetric sequence, which satisfies the mathematical relationship x of n is equal to x of minus n. What this means is that if we flip the signal horizontally only, and we get back the same signal, the signal is basically an even sequence. Any signal that is neither even or odd can always be broken up into a combination of even sequences and odd sequences. And this becomes even more evident when we look at the Fourier transform later on within the entire series. The slide just recaps what I just now said, but basically what we look at more is like when we're trying to break up signals into even and odd sequences. This actually helps us a lot when we go into signal processing operations later on within the course. These figures here basically give you an idea like how a periodic continuous time signal is represented. There may be some sort of property you may be able to take advantage of, being that it is periodic in nature, so there's going to be a assigned time period and an associated frequency and so forth. For a periodic discretized time signal, it's just that the signal needs to keep on repeating itself every t seconds, and this t here is referred to as our sampling time for discretized time. But what we watch here in particular for the discrete time signal is that even though we refer to t here as sampling time, we want to watch it with respect to n instead. So it needs to repeat after every n samples in order to obtain some sort of periodic time property itself. So for continuous time, a signal is periodic such that the x of t signal is going to be x of t plus capital T, where capital T is basically the period of the signal. For a discretized time signal, because we're not dealing with t and we're dealing with n, this means that x of n needs to be equal to x of n plus capital N, where capital N is the period in samples, meaning this is how many samples does it take for the signal to repeat itself. Capital N must be an integer. It cannot be a decimal, it cannot be a fraction. It must always be an integer. If we watch a continuous time signal here, we respect it if we're going to deal with a sinusoid signal, let's say a cosine signal. For every choice of frequency, this signal remains continuous and it will be unique depending on the frequency, meaning that we may have the signal represented at 200 Hz, maybe 400 Hz. It's still a sinusoid signal, but the frequency changes the property of it accordingly, making it unique. And because there's a frequency assigned to it in this case, and the sinusoid property is present here, it's going to be periodic for every choice of this frequency. However, when we go to the discretized time sinusoid, this does not hold true for the frequency. So if we represent our discretized time signal here for our sinusoid signal, and we observe the periodic property that we saw in the previous slide, and if we applied it here into this equation, you'll notice pretty quickly that we can't get back the original form of the equation for it to be the same in order to prove that it's going to be periodic. And the only way we can get this in particular is this capital N and capital F factor here needs to be equal to some integer here represented as k. And that's the only way the signal in discretized time is going to repeat itself. This means if we do a little bit of equation manipulation at NF equal k, we can actually solve for the discretized time frequency. But in solving for this also needs to be a rational number. So once NF is equal to k, where k is some integer, we satisfy the periodic property for discretized time sinusoid. Even though that we do experience a phase shift here with respect to theta. This generally isn't a problem with the signal, but it can be an issue later on if further processing can be done. And we will look at this later on in the course as to how we can accommodate for different phase shifts in discretized time. Now for a discretized time sinusoid at omega naught being our central frequency, if we phase shift it accordingly with respect to 2 pi, it's basically going to be the same signal, because for any sinusoid that we have seen before from previous knowledge, once it repeats every 2 pi cycles, it's basically the same signal. So this property holds true in discretized time sinusoids as well. Once the signal repeats every 2 pi cycles, it's just going to be the same signal no matter what. The reason why this is different to a continuous time signal is that a continuous time signal, if we add that 2 pi in, it modifies the frequency directly, meaning that instead of it being 2 pi ft and then we add that 2 pi, it doesn't phase shift accordingly. It might actually modify the signal frequency, so you might get a different frequency altogether for the same signal. So this repeated property that we observe here for discretized time sinusoids, it only applies to hardware or software generated discretized time sinusoids. And it won't work for something that is produced by sampling a continuous time signal. This only works in the hardware and software domain. If we actually sample a continuous time signal and we apply this, it generally will not work. So the discretized time sinusoid, as basically what we saw in the previous slide, at omega naught and omega naught plus 2 pi is basically going to be the identical same signal no matter what. But what we need to observe is what happens in between that omega naught and omega naught plus 2 pi. Actually, what happens to our signal frequency or the rate of oscillation with respect to discretized time. So if we start at omega naught equals 0, being that there's no centralized frequency, we basically have a DC signal. But if omega naught is equal to some known frequency, we basically can get this being represented as a sinusoid signal. So what happens here is that omega naught, the number of samples we get to represent this discretized time sinusoid, is going to be quite a lot, as you can see here on this figure. So that means we're going to be sampling like a whole set of samples just to represent the general shape of this discretized time sinusoid. But as we decide to move from omega naught and we go to omega naught plus pi, the signal frequency increases accordingly. So that way our sampling frequency increases accordingly as well. And that means because of the increase in rate of oscillation, we don't need so many samples to represent our signal. We can start using less samples actually to represent it. until we reach to the point when we hit omega naught plus pi, where we only need like 1, 2, 3, 4 samples to actually represent our signal, because we're fairly certain of this signal being a discretized time sinusoid. So as of such, when we move from omega naught to omega naught plus pi, the signal frequency is maximum at omega naught plus pi, meaning that we don't need so many samples to actually represent the signal in discretized time. However, when we move from omega naught plus pi to omega naught plus 2 pi, we get the reverse effect. Other that the signal frequency starts to decrease, meaning that we need more samples to actually start representing back our original signal. So instead of having these nice 4 samples here, we're now going to have to use more samples accordingly to represent our original content of the discretized time, so this is the discretized time sinusoid. And as of such, when we get back to omega naught plus 2 pi, it's basically the same thing as if we were at omega naught, meaning that we get back to the original amount of samples required to represent our discretized time sinusoid. So it is important to remember that this behavior that we just now observed for omega naught going to omega naught plus pi and then omega naught plus pi going to omega naught plus 2 pi only works on hardware or software generated discretized time waveforms. And it's quite different from when you're using continuous time signals or if you sample the continuous time signal. Mathematically, if we watch this with regards to discretized frequency, we can see here that discretized frequency, instead of being represented F, is represented as capital omega. And the omega naught here that we observe when we're modifying it, it tends to be distinct for distinct values or independent values of omega naught. But as we try to modify this capital omega here being discretized time frequency, it's not going to be unique for every choice of this discretized time frequency. And the period of n being, or discretized period here, it needs to be n omega, it needs to be equal to 2 pi k, and we saw where k needs to be a rational number or an integer in order for this to be satisfied in the previous slides. So discretized signals basically are stored as a sequence of numbers where each position of the number represents the n index, and the number itself represents the magnitude at which we captured at that particular index. The difference between indexes being like from n equal 1 to n equal 2 represents the sampling time, which is represented as capital T. So that means, let's say our sampling time was 1 second for any kind of continuous time signal that we're trying to get into discretized time. That means we will sample at the first second, then the second second, then the third second, and the fourth, and so forth. And because the spacing in between those two, any 2 samples is going to be 1 second, that represents our capital T being our sampling time. The common n represents each one of those samples. So the first sample was taken at t equal 1, the second sample was taken at t equal 2, and so forth. Now, because these discretized time signals are represented as a sequence of numbers, it makes manipulation of the signal a lot easier than doing it in the continuous time domain. This means we don't have to go through any continuous time integration, any continuous time differentiation or whatnot, because we're dealing with the signal itself as numerical values. It's quite easy to manipulate. So the next few slides actually show what happens if we try to have a 200 Hz signal and a 400 Hz signal being both sampled at 1000 Hz. And we're going to observe how many samples are measured per period in this case. So if we take our 200 Hz signal here as seen above, and we sample it at 1000 Hz, we can observe here that we get 1, 2, 3, 4, 5 samples for every instance of 1000 Hz. And this is quite true if we take the 1000 Hz here being our sampling frequency and divide it by the original frequency, 200, and we'll get 5, representing the amount of samples we get regarding for each instance of period of 1000 Hertz. If we take a 400 Hertz signal now, and we try to sample this at 1000 Hertz, what we observe here is that we only get 1, 2, 3 samples. And it's evident if we take 1000 and divide by 400, we get 2.5, but we need to round that up because we're dealing with integers. So 2.5 rounds up gives us 3 samples. One thing to note though is that these limited amount of samples here, if we try to reconstruct the signal, we're not going to get back our nice sinusoid here. It looks like we're missing some sort of information because we're not getting enough samples regarding this, and in particular because the 1000 divided by 400 gives us a decimal number, we get something referred to as less samples, being that we can't actually represent the signal if we decide to reconstruct it enough. We won't get an accurate enough representation. So, as discussed a little bit earlier, basically the 200 Hz signal has 5 samples for every cycle of 1000 Hz, but the 400 Hz signal has 3 samples for every cycle of 1000 Hz. In asking what would be the least number of samples required, this actually depends on how fairly certain we are of the signal's behavior. So if we know that basically the signal is sinusoid, we only need like about 1, 2, 3, about 4 samples required to represent a sinusoid signal in particular, because we only need the maximum peak, the zero crossing, the minimum peak, and then another zero crossing, and then the signal repeats itself accordingly. So for any sinusoid signal, the least number of samples required is always going to be 4. So we're observing here the 200 Hz sample signal and the 400 Hz sample signal, which will both sample at 1000 Hz. And we want to see what happens if we decide to reconstruct these signals using signal manipulation. Now if we take the 2 sample signals here, the 200 Hz and the 400 Hz here, and we do the difference, and we decide to reconstruct it, what we observe here is that when we reconstruct it from the discretized time version to the analog time version, it tends to be very linear with regards to the reconstruction. Now there are other methods where you can apply and you can get like nice curves and so forth and whatnot, but for the purpose of this course we will be looking at linear behavior, not non-linear behavior. So one thing to note is that when we subtracted the 200 Hz signals, the 400 Hz signal from the 200 Hz signal, we basically just watch the magnitudes at which of each of these indexes were, and we just took the difference accordingly. If a sample didn't exist, that basically means at that index it's just going to be 0. So we remain with the original content of the previous signal as of such. So keep in mind, after we had the discretized time signal here, and let's say we reconstructed it back into continuous time, this is what our signal difference will look like. If we did this only using continuous time, however, this actually is what's going to be our end result. Will bring us to the first point of using discretized time signals. It tends to be an approximation of a real-world continuous time signal. The more samples you have to actually represent the signal, the better the approximation is going to be. The less samples you have, the worse the approximation is going to be, so you get less accuracy accordingly. Now if we watch the same sample 200 Hz signal and 400 signals and we decide to multiply them accordingly and we reconstruct them, this is what our end result is going to look like. But if we compare this, as if we did the 200 Hz signals and the 400 signals and we multiplied in a continuous time accordingly, what you can observe here is the stark difference from continuous time and discretized time. In particular, what you note here is that we tend to lose a lot of the signal frequency content here because it's not represented. We didn't take enough samples in order to get this representation. So this is also an indicator of what the approximation effect looks like if we don't have enough samples to represent these signals. So the next few slides basically is going to show us some manipulation using the unit step. And the unit step tends to be quite important for most applications of discrete signal processing. In particular, for any musical notes or motor drive signals, we tend to use the unit step for troubleshooting purposes and so forth. So if we start with a general unit step sequence here, we can see that basically the unit step is defined for n less than 0, it's just going to be 0. But for n equals 0 and anything greater than 0, it's just going to be 1. In this figure here, if we watch it and we advance it by 3, meaning that will be n plus 3, that means we need to shift the signal to the left by 3 spaces. So 0, 1, 2, 3. If we folded the signal, on the other hand, what this means is that we first reverse the signal. So we go u of minus n, meaning that this content here now is on the left, and this content here is now on the right. So we flip the signal horizontally. Because it's u of n minus n, and then we add 3, that means that in that case, we shift this to the right, because we deal with minus n. The behavior changes accordingly if n is positive or n is negative. So if n is positive, meaning that it's positive n, then if we have positive n plus 3, it shifts to the left. If we have positive n minus 3, it shifts to the right. However, if n is negative, those shifts change accordingly as well. So if n is negative and there's negative n plus 3, the shift goes to the right instead. If it's negative n minus 3, the shift goes to the left. So basically, if we had these two random signals here, which would have been a general advanced unit step sequence and an inverted unit step sequence, and we decide to do some signal manipulation on these, what you observe is that basically, if we had an advanced unit step sequence and a delayed unit step sequence, the difference of these two basically gives us a rectangular window. And this rectangular window occurs in between positive 3 and negative 3. If we took this same rectangular window here and we multiplied it by n, this n basically changes from a constant behavior here to a linear behavior for the same indexes of n between positive 3 and negative 3. Downsampling in particular, when we observe this phenomenon, is that when we have a lot of samples here, we basically can discard some of these samples if we're fairly certain of the signal's behavior. So we don't need all these samples here to represent the signal. So downsampling is actually very good for when we don't require a lot of accuracy. We can maintain the same level of accuracy, but we don't need a lot of samples, thus reducing our space requirements. This actually is very evident true when you have a huge picture and you try to scale it down. You still maintain the same quality. Upsampling, on the other hand, tends to prove a little bit of a problem, because this means that you're going to have to guess what the information is because you had less samples to begin with and you're trying to fill in the gaps to get more samples. So upsampling works if you're also fairly certain of the signal's behavior, because that means actually we can interpolate in order to figure out what should be these values in between these samples. However, in some cases, like for this particular example, if you zero interpolate, it basically just adds zeros in between the signals. So unless you're fairly certain of the signal's behavior, and you actually can do some sort of guesstimation or linear interpolation or nonlinear interpolation, then you actually can get a fairly certain accurate representation. However, if you're not certain about the signal's behavior, it tends to produce some really weird effects. And this is quite evident if you try to take a small image and you try to enlarge it. It is quite blurry because the interpolation, even though it tends to try to do a lot of smart tactics and whatnot to try and guess what the information is going to be, it still does not do it accurately enough because it's trying to fill information that does not exist. So this brings us to the end of our first lecture. The next lecture is basically going to be the second recap to our signals and systems behavior, and we're going to be observing discretized time convolution in particular.